more or less this week conclude my quick recap of set theory and get into real analysis. So, which I'm just recollecting all the things in set theory which I will be using at some time or the other in the course. Okay. So we have seen a lot of things about countably infinite set, uncountably infinite sets, and so on and so forth. One of the major things that you should remember about these infinite sets is if you add two infinities, the bigger one will survive. And if both are of the same size, you will get the same size. That's like Aleph naught plus Aleph naught will be Aleph naught. Aleph naught plus 2 to the power of Aleph naught will be 2 to the power of Aleph naught. This principle will work, except when you are exponentiating, you will go one step further. Aleph naught plus to the power of Aleph naught will go to 2 to the power of Aleph naught, and so on and so forth. I will keep on using them whenever I want, instead of going on doing all those things in these. Whenever whatever is needed, only that part I will use. Okay. But whatever I have said about the power set, the set of all functions from A to B, their cardinalities, etc., I will be using them very often. I mean, to several instances. Okay. There is the other aspect of it which I would like to discuss, something about sets. Namely, we have already seen the notion of equivalence of sets. I say that two sets are equivalent if there is a 1-1 onto mapping from one to the other. This is a very, this should not be confused with the equivalence relation, because the business of set of all sets creates a messy paradox. So therefore, we will now look at the notion of equivalence relation in a more formal manner. Okay. So the next topic will be relations and various types of relations. So suppose I have two sets. I assume that almost all of you know these things, so it will be a quick review only. Suppose I have two sets, then a relation, the word relation itself says what it is, so I will make it in a more abstract manner. Any subset R of A cross B is called a relation from A to B. Any subset of A cross B. Okay, so we will make certain comments here. So you may say that the empty set is there. What do I do? The empty set is called the empty relation. Okay. And if you have the full 2 to the the entire collection of subsets of A cross B, that's called the universal relation from A to B. Okay. So that with those things in mind, let me make one thing clear here. So R is a subset of A cross B. So therefore, it is a collection of some ordered pairs where A belongs to set A and small b belongs to set B. So let R be equal to the set of all AB, where A belongs to a subset A1 of A and B belongs to a subset B1 of B. Okay, so it has to be within, the second coordinate comes from B and the first coordinate comes from A. Okay, so if an ordered pair AB belongs to R, we say A is R related to B. A is R related to B. Okay. Let me make a few more comments here. See, for example, if you take a function f from a to b and look at its graph, that's a subset of a cross b. And if you can look at the function also as its graph, so these are synonymous. So every function can be thought of through its graph, and therefore a function is also a subset of a cross b. So every function is automatically therefore a relation, but it is a very special type of relation. Okay, so every function from a to b is a relation viewed as its graph GF. The only thing to be noticed is this, for this particular function, for this particular relation, every a must be related to some b, because f of a must be defined for every a if a is the domain. So every a has a relative, and since it's whenever we say it's a function, it's a single valued function, not multi-valued, what we mean is every a has a unique relative. Okay, so that means for every a in a, there exists a b in b such that ab belongs to that function f. Now viewed the function as a graph, as a subset of a cross b, and ab1 belong to f implies b equal to b1. I am not saying a1b equal to a2b implies a1 equal to a2. I am not telling 1 1 or anything. All I am saying, the value should be uniquely defined. Okay, then b is denoted by f of b. That's our usual, coming back to the old notation. Okay, so every function is a relation, but relations need not be functions because they can be multi-valued. A fellow can be related to several people. Okay, so that's the difference between a relation and a function. Okay, I'll give you a number of examples which will appear in the course, in this course or in some other courses, but some may be trivial, but some other examples that I give will be for using in this course. Okay, more or less I'll be giving a number of examples which I use. One of the earliest examples is the following. Suppose you take, okay, yeah, well, let me make one more comment. If a equal to b, then any relation R is called a relation on A. Okay. Instead of saying relation from A to B, we say now it's a relation on A. So let's take the simplest examples where A equal to A for that part to start with. Let us take A equal to Z and then look at and let n be a fixed positive integer. Then we say let us look at the relation R to be all those AB such that A is congruent to B mod n. This is one of the earliest, simplest relationship examples. If the difference is divisible by n, I say A is related to B. If A minus B is divisible by n, then I say A is related to B, and this comes in many calculations in number theory. Let me give you more examples. Most of them I will give from A to A. Let omega be any set and look at A to be 2 to the omega, the set of all power sets of omega. So therefore omega is what is known as the universe of discourse. I am going to discuss only about subsets of omega, not all subsets of the entire world, but only subsets of a fixed set omega. There will be 2 to the power of the cardinality is 2 to the power of cardinality of omega, and what we do is now x y belong to A, we say x is related to y if the cardinality of x is equal to the cardinality of y. It is that equivalence relation now on this set A. Okay, that is x is, in the set theoretic language that I introduced, if x is related to 1. So the set 1, 2, 3 and the set A, B, C, if I take all the alphabets, English alphabets and all the numbers as my omega, then the set 1, 2, 3 and A, B, C will be related. But 1, 2, 3 will not be related to 1, 2, 3, 4. 1, 2, 3 will be related to 4, 5, 6 because the size is the same. This is the beginning where we had the equivalence of sets. Now let's look at this is the word is equivalence. I have a suspicion this is not the board. I should be very careful. Yes. Let me give more examples now. So suppose, okay, randomly I will give you examples. Let's take VB to be a vector space. I can't lecture without linear algebra. So V is a vector space over F. For some reason, I got stuck to this linear algebra. Okay. So V be a vector space over F, where F is a field. If you don't like, take it to be complex or real or whatever you want. Now suppose it could be finite dimensional, infinite dimensional. I simply don't care. Any vector space over any field F. Okay. So then let W be a subspace of V. So I have a vector space V, inside that I remember, I think Prayag is here. Prayag came to my office and said, sir, you draw more pictures, it becomes more clear. I told him, when you want to do analysis and abstract things, you avoid as many pictures as possible. See, according to Bertrand Russell has a very stinging criticism of Euclid about his geometry. He said, Euclid proves everything by drawing a figure. You can always draw figures to cheat people, so that it works, okay. And I think many graph theorists do it, okay. I know, I like to have dig with graph theories because that's one of the most difficult subjects in my opinion. But people try to get away with sometimes with drawing some very trivial figures. Okay. Anyway, I never said it, so yeah. In fact, there is one problem which myself and a friend of mine in the US are trying to solve using graph theory. By the way, this is not that I don't like graph theory. So let's take a vector space and take a subspace W, and now we shall define a relation. R on V as follows. It's a relation on V, therefore I must say how a vector x in V is related to a vector y in V. Okay. So for xy, okay, so I am going to take this relation. It should be a subset of V cross V. So I must take xy belong to V cross V, and then I will say x is related to y, provided what are the types of xy I take such that x minus y belongs to W. I am not claiming that x and y are in W. X and y are in V, but the difference comes down to W. As long as the difference comes down to W, this gives rise to a relationship, okay, between x and y. For example, just to visualize what's happening, let V be R3. Any example on vector space should manifest itself very clearly on R3. Okay. And let's take W to be the xy plane. The third component is 0. So let's take all that is obviously a subspace, because if you take any two vectors in the xy plane, the sum is there, a constant multiple is there. So there is automatically a subspace of the R3. And now what I am going to say is, I am going to look at the relation R to be the set of all xy in R3 cross R3 such that x minus y belongs to W. What does that really mean? The third component must be the same. Basically what I am doing is I am slicing the vector space as layers. Okay, the third component 0, third component alpha, third component beta, third component gamma, and minus alpha and minus beta. So basically this relation is slicing off, and everybody in one slice. I am horizontally slicing the third three-dimensional space, and everybody in one slice are related. Okay. So that's what this relation really means, and that slicing becomes slicing through W in a general case. Okay. And this slicing is very important. It gives rise to certain different structure of the vector spaces, which we will see shortly. Okay. But then R is a relation on B. What is the number? 3, 4, 5, n plus 1. Okay, that was 3. Okay, in vector space still. Okay, so now one more. Many things in vector space. Again, V is a vector space over F. So let B with set of all linearly independent sets in B. See, it's a set of all some type of sets. Each element of B is a set. Each element of B is a linearly independent set. Take every possible linearly independent set and take that whole collection of all possible linearly independent sets. That is the B for me. Okay, and define for xy in B. What does xy in B mean? X and y are linearly independent sets in B. For xy in B, define x is related to y if x is a subset or equal to 1. Okay. X is contained or equal to 1. That's another relation. Okay. And this relation is basically what we shall eventually use to show that every vector space must have a basis. Analogously, any question? Not subspace, subset. Either the linearly independent set X is the same as the linearly independent set Y, or every vector in this linearly independent set X also appears in the linearly independent set Y. It's a subset of Y, not subspace of Y, because I am not talking about subspaces here, only linearly independent sets. Okay, so that's a relationship. Okay. For example, in R3, if you look at x to be the, let me make it R2 to make life simpler, 1 0, and y to be the set 1 0 0 1, then x is related to y. Both are linearly independent set and x is a part of y, then x is related to y. But if you take x to be 1 0 and y to be 1 1, both are linearly independent sets, but neither is related to the other. So x is not related to y and y is not related to x. Okay. So this is a very important, the subset of, in the collection of sets, the subset of relation is a relation. Any collection of subsets you can take and put this relationship. I am particularly looking at it in the collection of linearly independent sets. Okay, here's one more example which I probably again use, which I already introduced, so I can do it. Okay. So let's take one more example before we proceed further. Let us take A, B any two sets. Okay. And let F be the collection of all functions from df, okay, from a from, how should I write it? All collection. Let me put a very peculiar notation. So let me take f to be the set of all functions from such that df is a subset of. Do you understand what it means? I am going to take all collections whose domain is a part of A and all of them have the same codomain B. We have seen this before almost in the first class. So I am going to look at all functions whose domain is a part of A and whose codomain is B. Okay. Then we say F is related to G if G is an extension of F. Remember what is meant by extension of F? The domain of F must be at most the domain of G. So domain of F must be contained in domain of G, and in the common part both F and G agree. Okay, that is a relation. So F is related to G if G is an extension of F, or also the terminology is F is a restriction of G. G is either an extension of F or you say F is a restriction. So we write this, remember we wrote this as this, G is a extension of F. This notation is in anticipation of what is going to come. So we can go on, but between you take any two sets, take any subset of A cross B, you are going to get a relation. So basically, therefore, suppose I have a set A whose size is M and B whose size is N, M elements and N elements. So how many relations can I define from A to B? See, every subset of A cross B will give me a relation. So it depends on the size of this. What is A cross B size? Mn. So 2 power Mn. Are you convinced? Okay. So but the moment these become infinite sets, there's crazy number of relations that are possible, infinite number of relations that are possible. So what we are going to do is, we are going to look at two types of relations. And the first one is what is known as equivalence. Equivalence relation on the set A. So A is a set and I have R, a relation on A, and we say that it's an equivalence relation. It obeys all those common properties that the equivalence of sets that we had. So okay, so R is, this is all common knowledge. If you don't know these things, never tell anybody that you don't know these things, because 10th standard students know these things today. I never knew it even after MSc, okay, but today 10th standard students know it. R is said to be reflexive if A or A for every A. Everybody is related to himself, okay. For example, if a relationship between people here is A is related to B, if A is the brother of B, then A is not related to A. Okay. Very simple thing like that. Okay. So you want to be reflexive if A is related to A. And it is said to be symmetric, that is if A is related to B and B is related to A, and so A is related to B if and only if B is related to. It should not be one-sided relationship. I call him as my friend, but he doesn't call me as my friend. That's a problem, okay? That's most of the time that is the problem. Okay, so anyway, so we would like to have symmetry. If A is related to B, B must also be related to A. And finally we say it is transitive. It's a disease that goes. If A is my friend, B is my friend and he is B's friend, he must be my friend. Otherwise he is in trouble. Okay. If A, B or C implies A or C. See, I remember this transitivity is a very interesting relationship which we exploited very nicely in our younger days. I don't know now with all the internet and email and WhatsApp and all, this has vanished, okay. In our days, when I first joined the institute, which was once upon a time in the last century, suddenly we would, the chairman, or in those days there was only one professor in each department. The head of the department would call and say, see, day after tomorrow, we have to give our report to the Ministry of, I was in Civil Engineering department, Ministry of Irrigation Power, you go to Delhi and present the report. The day after tomorrow, in those days, going to Delhi from Bangalore, the only way was you have to go to Chennai, which was called Madras in those days, change the train, get into another train, then go all the way into Delhi. There was a great train called the Grand Trunk Express, which took 56 hours to go from Madras to Delhi. And then there you don't know where to stay. So the thing started then. My friend has a friend whose uncle's brother lives in Delhi, and I will give you a letter, this is the address, you go. So his friend's relation, his relation became my relation, and very calmly I went and stayed with them. There was no other way, okay. So we exploited the transitivity extremely beautifully, okay. Whether they were transitive or not, we forced transitivity. I think probably I'm in a good mood today. This happened to me once when I was traveling in the train. Forget about set theory for a while. Enjoy life. When I was traveling in the train, I have a very peculiar background. My parentage is Maharashtrians, but I was born and brought up to high school level in Tamil Nadu and ended up in Bangalore. Okay. So the school education was in Tamil, so I also know how to read and write Tamil. So once I was traveling to Delhi, I was reading a book and there was a gentleman sitting next to me After a few days, maybe I should take a day, he started talking to me. He said, "You are reading this book, how do you find it? How do you like this book?" I said, "It's okay, but the author is not using good pure Tamil. He uses mixed words from Sanskrit, Hindi and other things. It's not written in a pure language." The man said, "Can you give me some examples?" Then I showed him a few pages where I marked in pencil and all these things. And then this gentleman patted me on the back. He was the author of that book. And the bonus was I got to stay with him in Delhi. Okay. So it works. The transitivity is a very, because I was related to the book and the book was related to him, I got related. Okay, right. All right. So if a relationship, if all these three are satisfied, that relation is called an equivalence relation. If R is reflexive, symmetric and transitive, it is called an equivalence relation. Just to start, let's look at that big example, one of the examples we had, V, and we had W, and we say X is related to Y if X minus Y belongs to W. Is this relation an equivalence relation? See, you see that X is related to X because X minus X is a zero vector, and the zero vector should belong to every subspace. Okay, so that's fine. And then if X minus Y belongs to W, Y minus X belongs to W because W is being a subspace closed under scalar multiplication. So it is symmetric. And if X minus Y belongs to W, Y minus Z belongs to W, that sum also belongs to W. So X minus Z belongs to W. So we use the fact that the zero vector belongs to W. We use the fact that W is closed under scalar multiplication. We use the fact that W is closed under addition. So the power of subspace is completely used, not even one thing is missed. Okay. So this is an equivalence relation. Is an equivalence relation. And each slice therefore is treated as one, can be treated as one object. Everybody there is related. You pick one fellow and study him, and you know that slice. So the vector space is studied in slices. Okay, that is what is known as quotienting. I will come to that shortly. Okay, so we have this. Suppose I have a relation which it is all these properties. What does it do? Basically, it sort of partitions the given set, and to study the given set, all you have to do is study one representative from each. As far as certain properties are concerned, they are all common. So in order to establish that, let me also give you some examples. Let's take for example, say CNN. What is CNN? The set of all complex n by n matrices. Okay, set of all complex n by n matrices. So I say a matrix A is related to a matrix B if there exists an invertible P such that P inverse AP is equal to B. This is what is known as the similarity relation, okay, between matrices. Then this is an equivalence relation. It's very easy to see. Because A is related to A, you can take P to be the identity matrix, I inverse A, I equal to A. Okay. So A is related to A. If A is related to B, B is related to A, put this P to the other side and called P inverse as Q, you get Q inverse B, Q is equal to this, and the same way with the transitivity also. This and now studying the set of all matrices with respect to this equivalence relation is all that linear algebra course. Diagonalizability, the diagonal form, the Jordan forms, etc., give the various equivalence bunches. Okay. So the whole, basically the fundamental idea in linear algebra is to study these equivalence relations. First basic theorems are. Okay. There is another way another relation, this is called similarity relation. I will say A is related to B if the row reduced form of A is the same as the row reduced form of E, the row reduced echelon form. Okay. Which means in the context of solving systems of equations, the system Ax equal to 0 is the same as the system Bx equal to 0. That's where the relationship is. And so the whole elimination and the solution of system is studied through this equivalence relationship. Okay. If you study the row reduced form, it's enough, you already studied the original form. This is another thing. The other relationship, see whether it's equivalence or not, I will leave it to you. If A is related to B, if there exists PQ orthogonal matrices, let's take unitary matrices in the case of complex, such that Q star AP is equal to B. What does that remind you? If you have taken a linear algebra course, this is the study of the singular value decomposition. Okay. Basically, this is what leads to the study of singular value. So the three chapters are, this one gives you the row reduced chapter or seen in the systems of equation. This gives you the study of diagonalization and Jordan canonical form, and this gives you the study of singular value decomposition. These three relations is the first three theorems of linear algebra. Okay, right. So now, what is this basic idea of equivalence relation? Suppose A is any set. Now we'll from now on denote an equivalence relation with this. Okay, instead of writing R. Whenever I write, that means that is a equivalence relation. This is an equivalence relation. For example, in classical geometry, congruence is an equivalence relation among figures in the plane. In particular, you say two triangles are congruent if something. How do you say two triangles are congruent? Okay, again a digression. Suddenly, how do you say two triangles? When do you say two triangles are congruent? If I just walk across and ask somebody in central school, they will answer quickly. So when do you say two triangles are congruent? Some yes, all these things. Yes. We always say yes to everything, you are safe. Okay, safe. So the side angle, and so on and so forth. There are many such ideas. So, but then this has to be done in a more formal way at a later stage. Okay, our man Bertrand Russell and real formal mathematicians won't agree. Okay, let's take for example, in geometry we introduce three transformations. One is translation, one is reflection, the other one is rotation. If I can make one triangle coincide with another triangle by applying a sequence of finite number of sequences of these transformations, then I say the two geometric figures are congruent. Okay, that's how congruence is defined. So it's not necessarily with respect to triangles. Any two geometric figures in the plane are said to be congruent if one can be obtained from the other by applying a finite number of sequences of these transformations. That's exactly what we do in the row reduced form. What are the three transformations we use? Interchange of rows, adding a multiple of one row to the other, and multiplying row by a constant. So there are three transformations we introduce. If one matrix can be obtained from the other matrix by a finite number of elementary row transformations, we call the two matrices are equivalent or row equivalent. We go on putting some uncle-aunt type relationship. This is also row equivalent type of relationship. Similarly, column equivalent and so on and so forth. So these are the transformations these transformations of translation, reflection and rotation define the equivalence relationship of congruence. But then we also study a chapter on symmetry. Two triangles are symmetric, the SSS is gone. They are called equiangular or whatever, the sides is in proportion, all kinds of ways we say. Again, in terms of transformation, what does it involve? These three plus one more. Uniform scaling or shrinking or contraction or expansion. So scaling, uniform scaling. It is not that I take a picture and just blow me up and show all the other fellows small. That is not symmetry. That is not a symmetry of geometric figures. I must blow that picture uniformly for all the people. Okay. And that's what the symmetry theorems are. When you go on adding more and more transformations, you get more and more geometries. Topology is to add some more. You add non-uniform contraction and non-uniform expansions also. So you take like a rubber sheet, you just hold it on place and stretch one part of it and keep it as it is. Then you get into the topological transformation, then the ideas of topological equivalence and so on and so forth. Okay, so basically therefore there is a group of transformations with respect to which these can all be brought together. So geometry, modern geometry therefore is the study of invariance of when a group acts on a set S. Okay, that's how geometry is studied today. Okay, anyway, so suppose therefore I have a set A with the equivalence. So the set A can be the set of all triangles in a plane and the equivalence relation may be congruence. Okay. And when I study high school geometry, they say the area of a triangle whose sides are ABC is given by square root of S into S minus A into S minus B into S minus C, whatever those S's are. Okay. And they never say if you draw that triangle there or the triangle here or the triangle there or this side or that side, because they are all congruent. They will have so in other words, all congruent fellows will have the same area. So it's enough if we study one of them. That is the fundamental principle when we do equivalence. Whenever you define an equivalence relation, in one somebody is equivalent to another fellow, there is going to be a common property and that's what we are interested in. And at the time therefore you don't study all of them, one fellow you study, then you have got all of them. That is what is known as an equivalence class. Okay. So then for any A, we define the equivalence class of A to be all those B's, all those X's in A such that A is equivalent to X. The equivalence class of A is all its relatives. The set of all relatives of A is called the equivalence class of A. The relation is through this equivalence relation. So for every element A, we define an equivalence relation. This is called the equivalence. EA is called the equivalence class corresponding to A, or equivalence class generated by A. Okay. Now you take this equivalence class, one thing is guaranteed. EA is non-empty. Why? Because A is related to A, so A will belong to E, because A belongs to EA. So every one of these equivalence classes is non-empty. Okay. The equivalence class corresponding to any number, any element is non-empty. And the second important thing is the following. Either if AB belong to A, either EA, AB equal to empty, they cannot have anything in common or everything in common. If you take two elements in the set A and look at the equivalence classes for corresponding to each one of them, either they don't have anything in common, they completely collapse into the same thing. This is easy to verify. I will just write this. So what is the consequence of this? Therefore, what I will do is, I will look at all the equivalence classes and I will take only the distinct ones. If A gives me EA, I won't take EB because I already taken because B is equivalent to A. So if what should I call it? E be the collection of all equivalence classes or distinct equivalence classes. Okay. Only the distinct fellows I take. I take an element, take his equivalence class. I take the next element. If his equivalence class is the same, I throw it out. I take next one, so on. So I take all the distinct equivalence classes. Then the dangerous word, clearly the set A is equal to the union of all E's, such that E is in this collection. Take all the union of all these distinct equivalence classes, then it is the whole set, because everybody is in one of the equivalence classes and everybody has been taken care of. All the distinct ones have been taken care of. And because they are distinct, EF belongs to E, E not equal to F implies E intersection F is empty. They are distinct, so they are not equal, but if two equivalence classes are not equal, they have to be disjoint. Okay. So this is what is meant by saying we have a partition of the set A. We have a partition of the set A into disjoint equivalence classes. So every equivalence relation gives rise to a partition. Therefore, remember a partition, just a partition, that's all. Take that fellow, split them into pieces, no two pieces have anything in common, all the pieces put together gives me the whole thing. That's all a partition is, okay. I don't want to make any political statement here, so what does he say there? Therefore, E gives a partition of. Conversely, if you have a partition, you will get an equivalence relation. How do I define the relation? Any two fellows in the same part are said to be related. That's all. That is the simplest way of getting. So every equivalence relation gives a partition, and every partition gives a equivalence relation. Okay. And now if you look at the vector space example, I said that I have a subspace and I say x and y are related if x minus y belongs to that subspace, then what does it do? In the three-dimensional case, one slice I took where the third coordinate is 0, that's the xy plane, and that is an equivalence class. Then keep moving it up and down, you will get all the equivalence classes. Okay. Let me give for example, so therefore example V W x is let y, x minus y belongs to W. How do the equivalence classes look like in this? There will be the subspace W shifted by one vector, shifted by another vector, shifted by another vector, and so they will all be shifts of the W vectors. In this, generally they are of the form W plus x or W prop some u. You take one u and shift all the vectors by u, just like taking that layer and pushing it up. And different shifts slowly will, if two shifts give the same thing, you keep it the same equivalence class. Okay. Take all such steps and then you can start generating a vector space out of these slices. Okay, so the big vector space now can be converted into a smaller vector space, taking the slices themselves as one unit and as a vector. So that's what is known as quotienting. Okay, I will come to the general idea of quotienting a little later. But right now, so now if we take E, okay, if we take the collection of all E, the equivalence classes, the distinct equivalence classes, this is denoted by the set A has been partitioned into these E sets by this equivalence class. This is called the quotient, A by the quotiented by the equivalence relation. Algebraists are very fond of these things. Okay. Let me give another example. Okay. So that you visualize what is happening. Okay. So suppose I give you, let's say FB, the set of all functions from 0, 1 to R. So the real valued functions depend on the interval 0, 1. So what does that mean? If you take a function, if you take the graph of the function will be something like this. Okay, the function is defined from 0 to 1. Of course, not necessarily continuous. I just draw the picture. Now I define an equivalence relation on this. Okay, I define f is related to g if and only if f prime equal to g prime. Let's say all differentiable functions. Okay, I should say more, but at the moment that's enough. Okay, let me not confuse you further. Sometimes ignorance is bliss. Okay, not bother about too many technical conditions. So what was the relation? So f prime is equal to g prime. Then I say f is related to g. Okay, obviously it's an equivalence relation. F prime equal to f prime. If f prime equal to g prime is equal to f prime. If f prime equal to g prime and g prime equal to h prime, f prime is equal to h prime. So it's a very trivial example of an equivalence relation. Now how do the equivalence classes look like? Suppose I take a function f, this is the graph. How do all the other fellows who are related to him look like? Just bodily lift him up and down. That graph will give you all the collection of all those fellows who are related to him. Therefore, one graph like this is enough. The rest of them are only linear movement up and down. Okay. So here, therefore, f is related to g if and only if g equal to f plus a constant. Because f prime minus g prime is 0, so f minus g must be a constant. So f must be equal to g plus constant, or g must be equal to f plus a constant. Okay. So that's a very simple equivalence relation, and we know how the equivalence classes are. Okay. So the equivalence class corresponding to f is the set of all functions of f plus c where C is a real number. Take all constant translation of the original form. If C equal to 0, you get F. So F is related to F. Okay. So every equivalence relation gives rise to a partition, and every partition gives rise to an equivalence relation. And once you have an equivalence relation, the common relationship that binds them gives rise to a common property. And to study that property, it's enough to study one representative from one equivalence class, and therefore you try to pick up the simplest representative. Who are the simplest representatives? They are the so-called canonical forms, like diagonal form, triangular form, or the Jordan form, or the singular value decomposition, and so on and so forth. But this canonical form sometimes is misused by in some. I remember in finite automaton, formal languages, etc., people use for the grammars like Greibach normal form, Chomsky's canonical form, etc. They are not canonical forms. They are not unique in that sense. If you give me a matrix, there is a unique SVD, there is a unique triangular form. If it is diagonalizable, there is a unique diagonal form. If not, there is a unique Jordan canonical form, and so on and so forth. But in many of these so-called canonical forms, they are not really indeed canonical forms. One could get different normal forms following the same procedures of reduction of the grammar. But sometimes be careful with these words, normal and canonical. But when a really classical analysis or a mathematician really uses these words, he really means an equivalence class, and from that equivalence class, the simplest representative. We simply, by looking at him, we can read off all the properties of that equivalence class. That's the basic point of that whole game of equivalence relations and equivalence classes. Okay. But an even more profound quote unquote relationship is what is known as the partial order. Okay. So the next type of relationship I'll look at is what is known as the partial order relationship. And then this will connect it back to us with set theory. Whatever we had discussed before, we talked about continuum hypothesis, axiom of choice, and all that. We'll come back, vector spaces, basis, all will be connected again one more time. Okay. The only difference between this basic difference between equivalence relation and partial order relation is whereas the equivalence relation is symmetric, the partial order relation is with a vengeance not symmetric. So what do we mean by that? So a relation R on A, on a set A, is said to be anti-symmetric. The word anti is a very dangerous word these days. Anti-symmetric if A is related to B and B is related to A. Symmetry said A is related to B, then A, B must be related to A. Such a thing can happen only when A equal to. This does not say such a thing happens when A equal to B. Okay, there is a difference between the two. This does not say that whenever A is equal to B, A is related to B and B is related to A. A may not be related to A at all. Okay. So this fellow doesn't say that whenever A equal to B, A is related to B and B is related to A. All he says, whenever that thing happens, this is the only possibility and no other case can happen. Okay. So this is called antisymmetric. Then R is a partial order relation on A if one reflexive to antisymmetric So in the equivalence relation we had symmetric and 3 is transitive. For example, let me give you two examples here to start with. Let us take the set of all real numbers to be our A, and then let us say A is related to B if A is less than or equal to B. A is less than or equal to B. Now let us see whether it is true. It is reflexive because A is less than or equal to A, either less or equal, equality is there. Antisymmetric, if A is less than or equal to B and B is less than or equal to A is equal to B. And transitive, if A is less than or equal to B, B is less than or equal to C, A is less than or equal to C. This is a model to start with, but don't get carried away by this model, okay. There are some things that happens with this model will not happen to others. So this is a partial order relation. On the other hand, look at omega, any set, and A to be 2 to the omega, the collection of all subsets of omega. Then I say X is related to Y if X is a subset of X is contained or equal to Y. Now this is reflexive because every set can be thought of as a subset of itself, and it is antisymmetric because F is contained in Y and Y is contained in X, then X must be equal to Y, and transitive because X is contained in Y, Y is contained in Z, then X is contained in Z. The law of trichotomy, this is also is a partial order. But given any two real numbers, either A is less than or equal to B and B is less than or equal, or B is less than or equal to A. Given any two real numbers, either A is less than or equal to B or B is less than or equal to A, which means given any two real numbers, one of them must be related to the other. Whereas that is not true here. You may have two sets, subsets, neither X is a part of Y nor Y is a part of X. I may have two sets like this, and that is omega. This is X, this is Y. Neither X is a part of Y nor Y is a part of X. So the law of trichotomy is not always necessarily true. Given two elements, this is the starting point. Given two elements in a, okay. So whenever I have a set A, I always denote the partial order like this. Okay, this is called a partial order, and then a set with this is called a partially ordered set or poset. For example, in the case of functions, we had this extension. F is a restriction of G, or G is a restriction, extension of F. That's a partial order relation and the collection of all those functions. Okay. So the extension problem is a partial order problem, and the set theoretic, and so on and so forth. The most important property in the partially ordered set is, given to any elements, there is no guarantee that the two elements will be related. Neither of them may be related to the other. Whereas in the case of less than or equal to relationship, that particular partial order, the law of trichotomy said that given to any real number, it's necessarily must be true that one of them is related to the other. The same is true if we take the relationship as the cardinality of X is less than or equal to the cardinality. Here, for example, I say X is related to Y. If the cardinality of X is less than or equal to the cardinality of Y, then Schroeder-Bernstein theorem and other things will give us exactly a partial order relationship. So, with respect to some relationship, I will have certain nice properties. With respect to some other relationship, I may not have the nicer properties. But what should be remembered is that when you have a poset, it is not necessary that two arbitrary elements need be related. Now therefore, we have to look at, well, the whole poset looks bad. There are fellows scattered around not wanting to talk to the other and so on and so forth. So at least let's take those groups of fellows who talk to each other. Okay, so at least there is some nice thing that's going on. They will be behaving like some more like numbers, right? We are very comfortable with numbers. I don't know how we are very comfortable with numbers because we don't know what numbers are. But somehow or other we are very comfortable with numbers. Okay, so they behave like numbers. Once I take a small group where that relationship says any pair one must be related to the other, then we are very comfortable. They are like numbers. They are like nice like numbers. Probably something good will work. So it is that type of collections which are called chains and so on and so forth, and it is the study of those which leads us to one of the most fundamental ideas called the Zorn's lemma, which is crucial in proving many existence theorems, and turns out to be equivalent to what is known as the axiom of choice. So what I propose to do in the next class is start with posets, look at what are known as chains, and look at certain things called upper bounds, lower bounds, etc. Words which will keep coming back again and again, and try to zoom as quickly as possible to the Zorn's lemma and the axiom of choice, and show using axiom of the Zorn's lemma or the axiom of choice that every vector space has a basis and every function has a maximal extension and so on and so forth. These maximal extensions are the most crucial ideas in analysis. Okay, so therefore I will just do this Zorn's lemma in the next class, doing all the preliminaries, and show how that is used at least in two different situations, and as we go along we will get familiar more and more applications of the Zorn's lemma. Okay, so the next class will be partially ordered sets and Zorn's lemma.